Hello, everyone. Welcome back to Codex. Today's speaker is Simone Brugiapaglia from Concordia University. Simone is a numerical analyst interested in analyzing and developing algorithms for deep learning, compressive sensing, and high-dimensional approximation. Today, he'll tell us about generative compressive sensing and deep, greedy unfolding for signal reconstructions. Take it away, Simone.
Thank you. Thank you, Michael. Thank you, all the organizers for the kind invitation. It's a pleasure to give this seminar. So the two keywords from my title are compression and depth. So this is motivated by the fact that I will illustrate recent research that happened together with collaborators, students, postdocs in these two areas, mainly compressive sensing and deep learning. So before I actually start with the actual talk, let me acknowledge all the wonderful people with whom I worked over the years and with which we kind of made this research that we'll be talking about today. So first of all, Ben Atcook is a professor at SFU. Aaron Burke is a former postdoc at Concordia and McGill. Matt Colebrook is a professor at Cambridge. Mark Iwan, professor at Michigan State. Yaniv Blanc, professor at UBC. Matthew Scott is a PhD at UBC. Xia Sheng is a former master student at UBC. Sina Mohammed Taheri is a postdoc at Concordia, former PhD at Concordia as well. Oscar Ilmaz is a professor at UBC, and Babur Roshi is a former postdoc at UBC. Also, let me acknowledge the different sources of funding that made this research possible here in the bottom. Great. So let's start with a very high-level motivation for this talk: compression, right? So it's not common wisdom that in natural images, the information hidden in the image is much smaller than the number of pixels. Perhaps this is kind of one of the most important motivations of this very seminar series called Codes and Expansions, right? So compression algorithms like JPEG are based exactly on this idea of expanding some signal in a clever basis, and then where you will have most of the coefficients being negligible so that you can discard them, you can achieve compression and have this kind of amazing results. Like if you store this picture from downtown Montreal where I live, there's a picture taken from a beautiful Mont Royal. It's a mountain in the midst of the city, very, very beautiful. If you come to Montreal, you can take this picture of the whole downtown. If you store pixel by pixel, it will take 9.5 megabytes of your storage. If you use JPEG compression based on wavelets, then all of a sudden you only use 7.9% of the storage. So, of course, the idea behind this kind of wonderful compression results is sparsity mainly. So perhaps everyone in the audience I don't know how many kind of early career researchers, students are there, but like the idea of sparsity is behind the compression. So we see that a vector is sparse whenever most of its entries are zero. So only a few non-zero. The spikes here, we're plotting the entries of a sparse vector, particular 10 sparse vector in a 100-dimensional space. And we have the L0 norm that counts the non-zero entries of a vector. But more generally, we have approximately sparse objects or compressible. How do we measure compressibility? Well, we'll have a set of S sparse vectors. So vectors that activate only at most S entries over an n-dimensional space. For example, this is the set of two sparse vectors in R3. And whenever you have now a generic signal X, you measure the distance of this X from this set of S sparse vectors. And that's called the best S term approximation error. Essentially the distance of this vector from this set. Of course, this is a sparsity with respect to the canonical basis, but real compression capabilities are achieved when you use kind of powerful bases such as wavelets, for example. So now you have a signal that you can express, again, codes and expansions, right? You expand in wavelets, and then the code X will be sparse, or compressible, and therefore that will give you the compression that you're desiring. So this brings us back to the golden age, what I like to think about as the golden age of sparsity. Once upon a time, maybe around the 90s, early 2000s, there was a lot of exciting research about wavelets. There were outstanding publications appearing those times. For example, this milestone of 10 lectures on wavelets by Ingrid Daubechy. I also like very much this textbook by Stéphane Mallat, Wavelet Tour of Signal Processing, where not only there's an introduction of the math behind wavelets, but also talking about many of their applications in signal processing. It was great times. However, that was, of course, not the end of the story, because David Donahoe in 2006 came up with very deep and interesting questions. Particularly, was asking why go to so much effort to acquire all the data when most of what we get will be thrown away? Can we not just directly measure the part that will not end up being thrown away? So in other words, if you're trying to acquire a sparse or compressible signal, let's say like in an MRI setting, you're scanning a slice of someone's body, instead of acquiring the whole image and then compressing it with JPEG or other compression algorithms, why don't we just measure the interesting part of the image, right? So the intrinsic information hidden in the image. That was the beginning of this method called compressed sensing. Then now here I summarize in a nutshell. Again, maybe this is going to be not needed for many people in the audience, but perhaps for some younger folks who are not necessarily seeing this field kind of being born and developing over the years. So in a nutshell, compressed sensing, now you want to acquire a sparse signal. Particularly, this could be a signal that is sparse with respect to some, for example, wavelet basis. Then you have a sensing matrix that kind of represents your sensing device. Could be, for example, an MRI machine, in which case the measurements will be Fourier measurements. And then what compressed sensing can achieve through randomization of the measurements, essentially, you can claim and prove that by using a number of measurements that scales only linearly with the sparsity of the signal and polylogarithmically with the dimension of the ambient space. So in other words, think about n as the number of pixels of your image and s as the number of important wavelet coefficients. So now you see the big dimension only polylogarithmically in the measurements. And if you do this with suitable random matrices, then you can also reconstruct the signal efficiently using, for example, L1 minimization. This is a very popular way to reconstruct signals from underdetermined measurements by minimizing the L1 norm. And the main takeaway is that the shape here of the L1 ball is really the key to promote sparsity because of this kind of diamond shape that will essentially will have your substrate will be tangent to the L1 ball at sparse vectors with very high probability. There's kind of a one slider on compressed sensing. Since sparsity, compressed sensing, there were two kind of very big research trends, so to speak, waves that generated a lot of great activity in applied math, signal processing, electrical engineering, and so on. However, then came, before that, actually, this had an impact on different domains. So before going to the other wave, this in particular had an impact on signal processing, I was telling you, but also machine learning. Perhaps the most important application of compressed sensing is compressive imaging, where the most successful application is MRI, compressive MRI. Also, the impact of compressed sensing went beyond just signal processing or engineering, electrical engineering. For example, here in this shameless plug, we have a book together with Ben Artko and Webster where we survey this field of compressed sensing used to approximate very high dimensional functions and to build so-called surrogate models. That's something that is very popular in fields like mechanical or aerospace engineering, where people have very expensive simulations and need to build efficient surrogates from very few samples to approximate the results of the simulation. So these are 4 textbooks that I would like to recommend, again, mostly to the most junior members of the audience. And this is really, so to speak, the Bible, Compressed Sensing, Mathematical Introduction to Compressive Sensing, this excellent book by Fukai Rahut. And these other more about applications of compressed sensing in different fields. So as I was telling you, there were waves, sparsity, compressed sensing, but then came what I think about as a tsunami, right? So there was the deep learning tsunami, then really kind of invaded many fields of research and industry. We're now witnessing the AI, the boom of AI, of which deep learning is kind of really a core, if not the core component. Everything perhaps began in around 2012 when there was a breakthrough of AlexNet, where state-of-the-art classification algorithms were substantially outperformed by deep neural networks. And then there came a sequence of more and more impressive breakthroughs where deep neural networks could achieve great performances in a variety of domains, from game playing to speech recognition to protein folding, computer vision, and then, of course, large language models where we can also chat with deep learning based models. So, and also very impressive awards, right? So pioneers for deep learning got the Turing Award in 2019, and then also there was a Nobel Prize in 2024. Just to make sure we're on the same page, I'm going to give some guidance to the most junior members. If you try just to Google on Google Scholar, if you look for deep learning, you'll be overwhelmed. There's an impressive amount of papers, and they grow as we speak. Two references I really like for as an introduction to the field. As first, this review paper, Deep Learning: An Introduction for Applied Mathematicians, published in Time Review. I think that's a very nice introduction for people who come from an applied math background rather than a computer science background. But also this is an excellent book that is actually under preparation, should be out pretty soon, perhaps this year, Mathematical Theory of Deep Learning. If you're really looking into you want to go delve deeper into the math details of deep learning, this is an excellent result that will tell you about from approximation theory to generalization bounds, all the properties of different architectures. This is a book by Philip Peterson and Jakob Zek. And yeah, I'd like to, again, perhaps this last slide is an overkill for most people, but just to make sure we're on the same page, we'll be talking about feed-forward deep neural networks. And what do I mean by this is the following. So we'll have an input x and then a function approximator, phi theta of x, where theta are some trainable parameters. And this function approximator acts in this way. So you first apply to x some affine transformation, then a nonlinear activation, then a fine transformation, nonlinear activation, and so on. You do that for up to some depth d for d so-called layers. And a very popular activation that people typically use is the ReLU. We'll also be using this talk for most of the results. So rectified linear unit that gives you essentially piecewise linear continuous function approximators. And the affine transformations essentially depend on trainable parameters that can be fit to data through, for example, the supervised setting through some MSE, mean square error minimization, where you minimize the training loss and you essentially try to find the network that best fits your labeled data. So with respect to sparsity, this is a much more complicated nonlinear model, right? So sparse vectors, the set of sparse vectors that we saw before is just a union of some linear subspaces. So in a way, it's perhaps one of the simplest nonlinear structures you can think about. But now deep neural networks can be much more complicated, right? Already, if you think about the range of a ReLU network, is not a union of subspaces anymore, but it's a union of polyhedral cones. And then if you have, also we have the compositionality of these networks that makes them really complicated and able to replicate and approximate very complicated structures. There's also an interpretation of networks as graphs when you think about the matrices and vectors defining their affine transformations, and that's why they're called networks. Then yeah, you usually minimize this kind of loss through some randomized stochastic optimization algorithm, such as SGD, if you want to take it simple, or keep it simple, or perhaps something fancier like Adam or other faster accelerated optimization techniques. Deep learning had an impact not only in all the applications we mentioned before, but also notably for this talk in inverse problems. So people started really heavily applying deep learning-based paradigms to solve the inverse problems, such as, for example, in medical imaging, right? So reconstructing an image from MRI data. Although this started roughly in 2015, although early works really date back to the 80s, there were already some early signs of ideas in this direction in inverse problems. And this is all great. However, there's kind of the other side of the coin here that is fundamental bottlenecks and fundamental issues with deep learning. In particular, they're, for example, vulnerable to adversarial attacks or so-called hallucinations. This is a recent paper where the problem of hallucinations in deep learning for medical imaging in studies where essentially deep learning-based reconstruction could add features that are not there. And of course, this poses serious challenges for making correct diagnosis. So this is all to motivate that there's a deep need in this field to come up with principled approaches, right? So deep learning paradigms that come in tandem with theoretical guarantees And this will be perhaps the main focus of this talk. So given this whole motivation, the goal of this talk will be the following. So I will illustrate recent results in signal reconstructions with techniques based on compressed sensing and deep learning. Essentially, we will combine these two paradigms and hopefully learn, while learning theoretical insights in this field. So we'll have two case studies. First will be generative compressed sensing, and the second one, deep greedy unrolling. I'll tell you more about each one of those. So essentially, will be two parts of the presentation going forward. And again, we'll focus on theoretical guarantees of performance. I didn't say that before, but feel free to raise your hand or ask any question also in between when I'm speaking. That's no problem. But when I'll transition from one part to the other, that will be also a good time to ask questions, maybe about the first part. Okay, so first part, generative compressed sensing. So let's first notice that the idea of generating, natural images with sparse linear combinations of wavelets or other powerful expansion bases, that's great. However, it turns out that you can represent some classes of natural images much more efficiently with deep generative networks. So this is an idea that started actually with the first architecture, such as the variational autoencoders in the early 2010s, or generative adversarial networks. These are networks that can generate images, okay? So for example, or other types of signals. Usually you have some sort of input, which is called of the decoder, which is called the latent code, and you randomize the latent code, and then they'll give you a random output that hopefully, if you train the network well, it will give you, for example, a random face, or perhaps a random scan of an MRI of a knee, perhaps, right? So depending on your data set, you can train a network to emulate random images of a certain kind. This was a website that back then when it came out, I found it pretty exciting. I think it's kind of, now I got a bit old, but like I think it's pretty cool. Like, this person does not exist. Every time you refresh the page, you'll get a new image of a person that does not exist, but it's generated by this StyleGAN architecture. This is very exciting, especially when it came out, because now some researchers started thinking, well, then perhaps we can do compressed sensing by using this kind of low dimensional hidden structure that depends on a deep generative network instead of using vanilla sparsity. And that's exactly the idea behind this kind of pioneering paper by Bora, Jalal, Price, and Demakis, came out in 2017, where essentially you implement compressed sensing where you replace the sparsity prior with the generative model prior, right? Instead of assuming that your signal is sparse in some basis, you assume that it's in the range or close to the range of a generative deep neural network. And this was an experiment from that paper where they compare, so using Gaussian measurements, for example, they compare compressed sensing with lasso reconstruction when you use a DCT basis or the wavelet basis as a sparsity basis. And this is compared with the generative approach, right? So this is compressed sensing with a generative model as a prior. And these are all reconstructions. On top, there's a ground truth, and these are all reconstructions with different methods. We can see that, for example, here was 4% of the measurements with images that have roughly 12,000 pixels, whereas classical compressed sensing can only capture very coarse versions of the images, very, very low frequency content of the image. With generative compressed sensing, all of a sudden, with this very low sample complexity, you can achieve decent reconstruction, and you can actually see something from the original image. So this was great, a great paper that came out in 2017, and it was a lot of follow-up work where people pushed on the application side, for example, applying this paradigm to optimize MRI reconstruction, or in general, achieving compressive imaging with generative models. But also in the field of scientific computing, people were using this to solve so-called parametric PDEs, where has to do more with applications in engineering, where it was mentioned before, where you have maybe a physical model that depends on some sort of PDE that is very expensive to solve. And you can also use generative compressed sensing there to build this kind of surrogate model to speed up the simulation time. So when we and some collaborators that I'll present in the next slide came to this problem, We thought, well, there's a clear gap between theory and practice. In particular, the theoretical guarantees here were done for Gaussian measurements. That makes the theory easier to kind of to analyze. However, in typical applications such as compressive MRI, usually assuming that you have Gaussian measurements, it's not a realistic assumption. For example, that's not what an MRI gives you. Usually, you have some sort of subsample isometry, such as subsample Fourier measurements. So we wanted to see if we could come up with theoretical guarantees for generative compressed sensing when the measurements come from a subsample Fourier, or in general subsampled isometry scenario. So the setting is the following. We have measurements of this form. B equals AX plus E. So A now is a subsampled isometry, is a random matrix that comes from selecting a few random rows of a square isometry. For example, could be, again, think about your MRI measurements. G is the generative model, okay? The input here, we'll be using generative models that have input space much, much smaller than the ambient space, such as the pixel space when you're dealing with images. We assume the unknown signal X to be either exactly generated, so lie inside the range of G, or being reasonably close to the range of the generative model. And of course, we want to achieve compressed sensing, so the measurement operator will be m times n, with m much smaller than n. Oh, sorry, this should be capital M. It's a typo. And some unknown errors corrupting the measurements, okay? Then how do you reconstruct, given those compressive measurements, how do you reconstruct the signal? Well, you perform the reconstruction in the so-called latent space, because now you plug x equals gz, and then you minimize this kind of least squares loss, or MSE loss, in Z, the latent code. So you find the best latent code that is able to fit the given measurements. You could do this, for example, with SGD, and then you just let your signal x hat to be the generative model applied to Z hat. Great. So before showing you the main theorem, I'd like to provide some definitions. So first of all, subsample isometry. There's several ways to define subsample isometries, but for the sake of keeping the analysis simpler, in this paper, we assume this random Bernoulli selector model. So essentially, we're tossing big N coins that, for example, you will have 1 with probability m over n, and 0 with probability 1 minus m over n. So in expectation, this will give you m measurements, and then you just stack the rows corresponding to the case where Bernoulli selectors are 1. This gives you subsample isometries that do not contain repetitions. For example, that's one of the advantages. And that's the process, right? So you start from, for example, a full Fourier transform U, and then you subsample with some Bernoulli selectors A. Also, we'll make some assumptions on the generative network. In particular, we will assume that all the transformations are linear, not affine, the intermediate layer transformations. It's not a substantial assumption, because you can always add so-called biases, so the additive shift by adding a 1 component to the input of each layer. But we assume this for simplicity, again, of the analysis. And then we have ReLU activations. That's a kind of a hard thing we need. At the moment, we don't know how to extend the whole theory beyond ReLU activations. And another requirement is that the network is so-called expansive. So from the input layer k-dimensional to the output layer n-dimensional, you have hidden layers whose size either stays the same or grows. So something like in this picture. Great. Another technical tool, which was the main kind of mathematical tool that allowed us to prove the theorem that I'll show you shortly, is the following: the coherence. So essentially, this is a generalization of the notion of coherence also arising in standard compressed sensing, but now we don't have sparse vector in particular to represent the signal. We're not using a linear model, we're using a generative network. So we consider this coherence that is with respect to a generic set. Okay, we will have a unitary transformation U, a given set that could play the role, for example, of your range of the generative model, or something close to that, as we will see. And we would say that this set is alpha coherent with respect to this isometry if the following holds. Essentially, if you can bound from above all the inner products, absolute inner products between your measurement bases, so the rows of U with unit vectors in T. Okay, so think about this image. Now that's a bad case where if T was this red set, this would have very large coherence. We would like the coherence to be small for our analysis. There will be very large coherence because essentially you'll have, okay, yeah, T is orthogonal to U2, but however, there are vectors in T that will be perfectly parallel to U1, so that gives you maximally coherent structure. Instead, we would like something that is as incoherent as possible, so as low as possible for alpha. So something ideal here in the setting will be something like here in between. So this tells us intuitively that essentially the measurement, so there's no measurement that totally misses information about T, right? So for example, the measurement U1 here is great for the set T. However, the measurement U2 being completely orthogonal to T will capture essentially nothing about T. So this is the kind of geometric idea behind this. So we would like the measurement vectors and the set to be in such a positions that when you then randomize the measurements with high probability, you get something meaningful. You still have enough information to perform the reconstruction. So another technical thing that we need before the theorem is the piecewise linear expansion. So first of all, let me note that the range of a ReLU generative network is a specific structure, is a finite union of polyhedral cones. But also whenever we'll have a finite union of cones, we'll define this piecewise linear expansion. That is the union of the span of each cone, okay? So the minimal union of subspaces that contains essentially this union of cones. And this is an illustration where there's a union of cone made by this dark blue cone and in particular this line, which is also a cone. Then the span will just be this plane union with the line itself. Great, so we have all the ingredients to present the first result. This was in collaboration with Aaron Burke, who was a postdoc, Concordia McGill, and with the group from UBC, led by Yaniv Plan and Oscar Ilmaz. So this is a theorem. So if you define the set depending on the range of G, so this calligraphic G is actually range G minus range G. You take the piecewise linear expansion of this set, as introduced below. If this is alpha coherent with respect to the measurements in the isometry U, and if you have the following sample complexity condition, so if M scales like alpha squared times N times K, remember N is the ambient space, K is the dimension of the input space up to log factors, then we have successful recovery. In particular, if you optimize that least squares error up to some epsilon opt tolerance, then you can recover an approximation to your signal X that is bounded, whose error is bounded as follows. So the approximation minus the ground truth is bounded by the best approximation error of X in the range G. So that's analogous to that best system approximation errors we had at the very beginning for sparse vectors. However, now you have a measure of how far you are from the generative model. Then we have a modeling error that contains actually a mixed information, both about the generative model and about the measurements, because that's the length of the projection error measured through the subsample isometry. Then we have the norm of the noise affecting the measurements and the optimization error. So this is now the recovery guarantee that, for example, in the specific case where your signal exactly lies in the range of G, then these two terms will disappear. For example, you'll just have something that scales like the norm of the noise and the optimization error. So, by the way, if you have any questions so far, feel free to ask them now. Good. Also, I cannot see people. Are you guys there?
Yes.
Yes.
Good, good,
Yeah.
great. So because I cannot see people, so I'm still online. Great. All right. So how to go beyond this? Actually, this could be improved substantially. First we apply this to a specific setting. There's this mystery of the coherence, alpha squared. Actually, if you look at this estimate, you might actually be this might make you raise your eyebrow, right? Because there's a scaling linear with respect to the big dimension n, and that's not good, right? But the point is that it's possible to achieve a coherence that is so small that this term will be essentially be canceled. And that's a setting where we achieved to prove this, particularly if you have a generative model where we assume a random last layer. So we'll assume random IID weights for the last layer of the network, and the other weights of the previous layers could be anything arbitrary and fixed. Then with high probability, this set piecewise linear expansion of range G minus range G can be proved to be alpha coherent with respect to U, where alpha is bounded as follows. Okay, so essentially after some simplifications, you can claim that alpha scales like square root kd over n. And that's exactly what you need, because if you combine it with this, that big N goes away and you find a scaling of k squared, so the dimension of the input squared times the depth of the network squared up to log factors. Now, interestingly, we still have a squared. We believe that's kind of due to the so-called coherence bottleneck. So probably there is, through arguments that do not rely on the coherence, there is a way to, excuse me, there is a way to get rid of the square, but that's an open problem at the moment. And that's possible, by the way. That's possible to get something that scales linearly in K in the Gaussian case. But for subsample isometries, currently is not clear how to do it. Some numerics to show that this coherence quantifies the quality of, it's a real parameter that actually captures the quality of approximation of your generative compressed sensing scheme. Here we have a phase transition where we plot the probability of success for recovery, the probability that the relative error is less than 10 to the minus 5. And we plot this in this space where we have a coherence on the x-axis, actually an upper bound to the coherence. That's kind of a technical thing, because estimating the coherence for an actual network is not something trivial, but we do propose a method to do that, to give an approximate upper bound to the coherence that relies on the QR decomposition of the last layer of the network. So if you have this phase transition, so coherence, large coherence means worse recovery. So probably the recovery goes to black, so towards 0. Low coherence, better recovery, so white. Also number of measurements, again, more measurements, better recovery, less measurements, worse recovery. And this shows that there is a relation between coherence and number of measurements that we would expect, like from our theory. Also, you can plot the relative reconstruction error as a function of the coherence upper bound. And again, you can see that the larger the coherence, the worse the reconstruction error gets. So these are individual runs of some compressed sensing, a generative compressed sensing experiment on a simple case with MNIST. And this is like the average recovery error. Also, by the way, in the paper, we propose a regularizer based on the coherence upper bound. So potentially you could also train your generative model G in a way that keeps alpha small. So in a way, you're optimizing the training of your generative model to achieve optimal compressed sensing with respect to some particular measurements. Okay, so maybe you want to optimize G with Fourier measurements, or maybe with hard measurements, or anything else that you might have in your application. Now you can do it by keeping the alpha small during the training, thanks to this regularization approach. You can also go beyond, you can do better than this and go beyond uniform random sampling with this Bernoulli selectors and IID Bernoulli selectors according to the same probability of getting a 1 or 0. You can do better because there's an intuitive property that is actually you should prioritize certain measurements that are, for example, if you're dealing with Fourier, you should prioritize low frequency measurements because they much more strongly correlated with natural images than high frequency measurements. So how to achieve that? Well, you can also use local coherence. Again, this is a notion whose idea is very popular in compressed sensing. We just applied to the case of generative compressed sensing, where now you have local coherences for each single measurement. Okay, instead of taking a max and a sup, now you just take a sup over piecewise linear expansion of your set T for each measurements over the inner products, absolute inner products against unit vectors in your set. And now if you do this model adaptive sampling, where the probability of sampling the measurement uj scales proportionally with the alpha j local, so the jth local coherence squared, you can show that you have probability like before with the same error bound if your measurements scale like the L2 norm squared of the local coherence times the dimension of the hidden space, the input space times the depth. So particular, this is a strict improvement with respect to the kind of global coherence approach, because global coherence is nothing but the L infinity norm of the vector of local coherences. And of course, the L infinity norm is in general could give you something much larger than the 2 norm squared. And the previous bound was essentially something that was scaling like alpha squared, so the L infinity norm of alpha log squared. So this is a strict improvement going from global to local. And you can see that this gives you benefit also in practice. This is a measurement with more interesting signals than before. We were training a generative model with the Celeb A data set of faces of celebrities and recovering them from 2D DFT subsample measurements. Okay, so first of all, you have to compute the local coherences, and you can estimate them numerically based on essentially random sampling the generative model. If you plot the local coherences in the DFT, in the frequency space, you'll get something like this, okay? This makes sense because it tells us something that tells us that we should sample more, so the density is higher here, close to the origin. We should sample more closer to the origin, or also to the axis in this case. And then somehow there's a decay law. Of course, there's some of these nonlinear features there due to the fact probably that the range of the generative model is very complex to capture. So, but this is a comparison between uniform and model adaptive sampling. Okay, so here we just sample uniformly in the Fourier space. Here we sample according to these local coherences. And now all of a sudden you can capture the ground truth with much, much, much better sample complexity. Okay, here we capture a decent approximation of the ground truth with 0.024% of measurements. It's very, very low sampling rate. And in uniform sampling, you need 6.25%. Okay, similarly for the signal, 0.024, an okay approximation, 0.098, very good approximation, but with uniform sampling, you need to go to around 6%. Also, there's a strong connection here. This is a particular case of something called generalized Christoffel sampling that was also studied by Ben Atkin, who gave a talk in this series, I think, a couple of weeks ago, Juan Manuel Cardenas and Nick Dexter, 2023. Another experiment, uniform versus model adaptive sampling, just to, again, as a sanity check to show that not model adaptive sampling can give you much better results in terms of number of measurements than uniform sampling with subsampled isometry. Here we plot the reconstruction error as a function of the number of measurements. Blue is model adapted. You can reach convergence much sooner rather than uniform sampling if you are in range. Okay, so this accuracy 10 to the minus 3 around, very, very good. Out of range is a much more challenging case. Like recovering images that are genuinely out of range is more challenging, but still you can see the benefit of uniform versus model adapted strategy, and also the same for the recovery, the probability of success. So recovery rate for model adapted or uniform, the probability of success gets higher much sooner than uniform. So to conclude this first part, we have proved the first recovery guarantees for generative compressed sensing with subsampled isometries, thanks to this notion of coherence for sets and isometries. And you can improve performance using model adaptive sampling. There's some important open questions left to investigate. For example, the optimal sample complexity. We think this should be something linear, like in the Gaussian case, but the coherence-based approach, unfortunately, doesn't show this. We have k-squared. So there seems to be a coherence bottleneck that is also present in compressed sensing here. Also, ReLU activation, our arguments heavily rely on ReLU activation or any other kind of piecewise linear activation, because we use the fact that the range of the generative model is a union of polyhedral cones. and then we take this kind of span of this set. But if you have other activations that this structure, this geometrical structure is lost. So like with the tan H activation, you'll have to come up with something different. So maybe do some sort of linear approximation of that. Also, we say nothing about the optimization. Our recovery guarantee say something about the minimizer of the training program without telling us how do we compute an approximation to that minimizer. But of course, that's a very relevant point to study as well. And yeah, applications beyond imaging, I think there's room to apply this paradigm to more problems. So if there's something where you would like to replace your sparsity assumption with a generative model, I think this paradigm could be very successful. So that's a good point for me to stop and maybe ask if there's questions about this first part. And sorry, I have a little bit of cold, so yeah, need to blow my nose. Any question on this first half? Chat is okay. I cannot see the chat, unfortunately, so
we will read if there's a question in the chat.
good. All right. Also, how much time do I have left, more or less? Like 10? 10 is okay,
Yeah.
10 minutes? Okay, perfect. So the second part is much shorter. So I'll give you some elements of this other idea where compressed sensing and deep learning kind of come together, and also to produce some theory about this with this idea of deep greedy unfolding. So first of all, algorithm unfolding. So we talk about compressed sensing reconstruction, and you can achieve compressed sensing reconstruction not only with L1 minimization, but with many other algorithms, such as greedy algorithm, orthogonal matching pursuit is a very popular one, or iterative hard thresholding is another very powerful iterative algorithm. And these have nothing to do with L1. So there's really different approaches. However, they can successfully recover sparse vectors from compressive measurements. And there's also this idea of unfolding iterative algorithm into neural networks. So the idea is that once you have like an algorithm that produces, subsequent approximations of some vector, for example, you just unroll the iterations of this algorithm and you interpret them as layers of a network. And then the point is that if this whole unrolled architecture is trainable, for example, in a PyTorch implementation, then all of a sudden this opens the way to do many interesting things. For example, you can optimize the performance of your algorithm to a specific data set. Maybe you want to personalize your algorithm to a medical data set. Or on the other hand, you can actually train architectures that are principled, that are inspired by some algorithm that we know. Perhaps we know theory from OMP or IHT. So certain properties will propagate from the original algorithm to the network. So this is a field that has been studied in the compressed sensing literature, and you can, for example, prove accuracy and stability result for these unrolled networks where you essentially translate the compressed sensing theory for the algorithm to theory for the network. So here we will focus on the greedy algorithm, OMP. Particularly, I will show you quickly a weighted variant of OMP. So the idea of OMP is very simple. You start from the zero vector, and you add entries to the support that initially is the empty set. How do you add new entries to the support? Well, you find the index of the column that is of A that is mostly correlated with the current residual of the given approximation xn. Plus, you might have some weights that try to capture the structure of the problem in the ambient space. So these weights, usually this is a diagonal matrix that kind of prioritizes certain indices with respect to others. And then once you have picked the new index, you add it to the support and you do a least squares projection over the current support space, okay? You just do least squares with the support is restricted to be in the current S n plus 1. So this great algorithm, however, unrolling it poses some challenges, unrolling it or some algorithms like this, like COSAMP or even IHT. The problem is that iterative and greedy algorithms like this depend on some sorting operations, okay? Here there's an argmax. In other cases, there's a thresholding step, maybe hard thresholding step where you keep the k largest entries of a vector. There's all these sorting operations that unfortunately, so sorting is a discontinuous operation, hence non-differentiable. It's really impossible to make it trainable through PyTorch if you just write sort something. And this kind of constitutes a bottleneck for which, because of which, greedy and iterative algorithms weren't unrolled up to a couple years ago. So we thought, particularly my former PhD student Sina, now postdoc, thought that we could relax the sorting operation with another operation called a soft sort. Soft sort operator is something proposed in 2020 that essentially an approximation to sort that now makes it a continuous function. And it also becomes numerically differentiable. So this is the illustration. For example, the first entry of a sort V for a particular vector looks like this. This is piecewise linear. The soft sort will look like this. But also, more importantly, arg sort. If you take the argument of the sorting operation, you have discontinuities. But now if you relax the soft sort, you have all of a sudden something that is smooth that you can now give to some sort of training algorithm and differentiate. So to give you an illustration, usually the sort, if you sort a vector like 3, 4 to 1, of course, the sorting will be 4, 3 to 1. Arg sort will be, first, second index, then the second component, then the first component, then the third component, then the fourth. And usually this will correspond to a permutation matrix. With the soft sort, that permutation matrix is approximated by essentially a stochastic matrix. Okay, row stochastic matrix where now each row will sum up to 1 and where the peak of each probability distribution will approximate where the corresponding one of the permutation matrix is. For example, here will be the first one should be in position 2, and now the highest entry is in position 2, the first one should be in position 1 for the second one, and so on. So 3, 4. So this is a continuous and numerically differentiable relaxation of sort. So we reformulated OMP in a way that we call like permutation or projection matrix based. Where essentially you need to reformulate all the steps in a way that makes it implementable in for example, in PyTorch and then differentiable. And this is achieved by representing the supports with a bunch of vectors, and we just extract the first row of each of these permutation matrix to kind of add the new index. And now instead of adding the actual, so when you do hard OMP, you would pick exactly one index, but now with the soft sort, you kind of pick a probability vector that tells you that there's high probability that the new index will be, for example, J as opposed to K. And then after you do that, instead of the restriction, we use this now approximate permutation matrix pi tilde to restrict to the current support, and then we do least squares, and this is a differentiable operation because you can apply, for example, Richardson iterations or conjugate gradient, and you can actually differentiate the corresponding approximation. So that is soft OMP because we replaced hard sorting operation with a soft sorting operation. Moreover, we have rewritten it in a way that allows for implementation as an architecture. So this makes the algorithm unrollable. So since I have 3 minutes in the interest of time, I'll maybe just tell you quickly about this. The recovery guarantee, we can first prove that soft OMP converges to OMP. Okay, when there's this temperature parameter tau that defines the soft sort operation. And when tau goes to 0, soft sort converges to sort. And also you can prove that, of course, asymptotically, soft OMP will converge to OMP, and that's easy to prove. However, you can also have a non-asymptotic convergence result where we give an upper bound to this temperature parameter that will be small enough to achieve accuracy epsilon between the soft OMP approximation and OMP, where this epsilon is an arbitrary accuracy. And we have this object called G1 to N or GI. These are the gaps. So the convergence will depend on these gaps between the selection vectors that are used in OMP. Essentially, whenever we take an argmax of a vector, depending on how wide is the gap between the max and the second biggest element. This will define the gap, and like when you have very, very small gaps, the problem becomes more challenging. So you need a smaller tau. Although numerically, if tau is too small, then you get a problem, because when you try to train the network with a very, very small tau, effectively you have like effectively some non-differentiable object. It will be really hard to get training to work. So here there's a trade-off. Tau needs to be small enough so that soft OMP is close enough to OMP, but also large enough so that numerically you can actually train then the resulting soft OMP. Here we show the convergence of soft OMP to OMP. This is the gap between the two for different number of iterations. So this is a convergence at 5 iterations of soft OMP to 5 iterations of OMP, then 10, then 15, then 30. The more iteration you want, the smaller the temperature parameter needs to be. That is also in line with our theory. And finally, some quick numerics about soft OMP and like the resulting network that it comes from training soft OMP that we call OMP-net. Essentially, we show that you can learn weights. You can learn the optimal weights to identify some hidden structure in a data set. For example, here we were generating sparse vectors where the components were only the first few, and then the optimal weights are able to find out that those are the important components. And in particular, this allows you to train a network that can outperform vanilla OMP by several orders of magnitude if you have very, very, very few measurements. Because now the trained soft OMP will be able to squeeze all the performance possible from the data set, rather than just having something that works for every S-sparse vector. So this was a comparison between OMP-net and OMP. And finally, you can also perform, this is something we're still working on these days, you can also perform dictionary learning with soft OMP and OMP-net. In particular, you can now learn the whole dictionary if you put just the network here, the unrolled network here. This is your expansion dictionary, and then you just train this guy on Psi. And in particular, we found out that it's really key to some kind of coherence-based regularization that was proposed a couple of years ago. But this works. So you can also train whole dictionaries with OMP-net. For example, here we approximate a dictionary that was a mix of DCT and identity, so cosines and spikes, but also real-world data. We can learn a dictionary and outperform normal OMP reconstruction on ECG type signals. So to conclude the second part, soft sort allows to unroll greedy and iterative algorithms that depend on non-differentiable sort operations. We prove that soft OMP converges to OMP, and also OMP-net can be used to learn weights or dictionary from data. You can also unroll other algorithms that I don't have time to show it here, but IHT or median recovery, some other iterative methods that can be unrolled. So we have a paper in progress where we are comparing different unrolled strategy and also prove some theory for the other unrolled algorithms. There's a big kind of question of, okay, can we prove any recovery guarantee now for the networks that we achieve after training? That's a big open problem that I think is very interesting as well. So I'll conclude here. Thank you very much for your attention. This is the main papers that I've been talking about today. Thank you.
All right, everyone, let's smash that reaction button.